Good afternoon, everyone. Thanks for attending CED's webinar today. In this week's installment of our webinar series that we've been doing the last few weeks, today my esteemed colleague Bill Daly is going to be discussing a project in which CED remotely controlled a 19-foot boat to run tests for the U.S. Coast Guard. My name's Tony Gandolf. I'm the Director of Business Development down here in South Florida. I cover the southern half of Florida for CED. Bill Daly, who's going to be doing most of the engineering and the engineer talking and knows way more about the topic than I do. He's a senior marine and mechanical engineer at CED Technologies and has over 24 years of distinguished background in forensic engineering in such areas as safety operations, operations of mechanical devices, recreational boating, and marine operations. A former U.S. Navy commander, Bill holds a Bachelor's of Science degree from the United States Naval Academy and is a Master of Science degree from the Naval Postgraduate School. Just so, as everyone knows, just as a reminder, feel free to ask questions throughout the presentation using the chat and Q&A features in Zoom. And with that, Bill, feel free to take it away.
Thank you, Tony, and thanks for everyone for joining us. I see at least one of the participants is a familiar face. In fact, he was active and actually helped us on the test day. So good to have Brian Goodwin on the webinar. So we were asked by American Boat and Yacht Council, ABYC, to assist them in looking at dynamic instability of what we call a Texas flats boat. Now, ABYC's work was through a grant from the Office of Boating Safety of the U.S. Coast Guard. And there were reports that these boats had some problems. They were described as, the technical term, dynamic instability, but they would swap ends, they'd spin out. The bow would very quickly, you'll see in some videos, very quickly move to the stern, so 180-degree spin. And this happened very, very quickly. The boat would not only swap ends, but would decelerate very, very quickly. So we looked at this and we said, well, what do we know and what don't we know? Well, what we know is what the Coast Guard reported to us. And that is what I said, that these boats are swapping ends and at times ejecting people, producing injuries and death in cases. And you'll see when we go through this how that actually happens. So that was what was known. That was the easy part. The unknown was the operating parameters of this boat. They were largely unknown. We could theorize what they were doing, but we really didn't know. We didn't have any data. We had reports and had no reason to doubt that the reports were anything but accurate. But we didn't have a feel at all for what this boat really did to get up to the point where it would swap ends and under what conditions that would happen. So let's talk about the boat.
Bill, I got a quick question.
Sure.
How do we get involved with our relationship with ABYC in this testing?
That's a good question. ABYC is also in Annapolis, Maryland. That's where I'm sitting right now. Okay. And we have been associated with ABYC in various ways for quite a few years. This opportunity came along and ABYC asked us if we could assist them in carrying out this study for the Coast Guard.
Okay, thank you.
So here's the patient. This is typically what we call a Texas flats boat. If you look at the picture on the left, you see it kind of looks like a traditional V-shaped hull. But right about where that wheel is located, it's not traditional anymore. So let's take a look at the picture on the right-hand side. About starting a third or 2/3 way back, about where that wheel is on the trailer. There, the boat flattens out and you have a tunnel. So you'll hear me talk about this tunnel, that's what I'm talking about. And you'll hear me talk about low gunnel height. And we'll get back to that with the details of that. But just, I figure a picture would be a good way for those of you who may not be familiar with this boat in particular, what we're talking about. So I talked a little bit about this. It's not a traditional hull form. It's a high bow, and as I mentioned in the previous slide, the center keel goes approximately 2/3 the way back. And then about where that, where that wheel was in the trailer, or approximately where one would sit at the center console, that keel ends. And what replaces it is a flat portion of the hull with a tunnel. And in addition to that, the gunnel heights are 4 to 7 inches. Now you can start adding these things together. If a boat starts to spin and you only have a gunnel height of 4 to 7 inches, that can become a problem. And you'll see exactly what problem that is in a few moments.
Bill, I got another quick question, Bill. I was curious, who makes these Texas flat style boats that we're discussing? Like, who is the manufacturer?
That's a great question. These are short run boats, meaning they're not, it's not a big production run. They're not your legacy manufacturers. They're typically, I don't want to use the term a mom and pop shop, but I think that adequately describes the difference between this type of production run and say a legacy manufacturer. So they're not your traditional manufacturer, and with that perhaps come other problems.
Okay, thank you.
So here was the challenge. You've kind of probably already figured out what the challenge was. How do you safely test a boat that you know is reported to be unstable? So we don't want to injure the participants. That would be really bad. We certainly don't want to cause property damage. That's not good either. And we don't want to create problems on the local waters. There could be any number of problems. Striking other boats, boats swamping, fouling the waters, all those things we wanted to avoid. So we knew it was a problem, the directionally unstable boat, and we wanted to figure out how to do that safely. So here's how we did it. There may have been other ways to do it. I'm told that other ways were tried on other opportunities and they were not successful. So I'm also told that we were the first company to successfully take a 19-foot boat and completely run it autonomously. And how did we do this? Well, we first started out, we wanted to figure out what is this hull that we're dealing with. So with the aid of our naval architect, we digitally mapped the hull using a 3D scanner, determined the center of gravity, just to get an idea from a naval architectural perspective, what are we dealing with? We didn't have that data from the manufacturer, so we had to create that data. Then we said, well, we need a test protocol, and we don't want to be in this boat. We made that decision because we knew it was directionally unstable. That's what was reported to us. And if boats are swapping ends, we didn't certainly want to be on board. So we designed and tested a protocol or a system to remotely control this boat. So if you look at that photograph, on the left-hand side, you see a sprocket with some chain drives. It looks like a bicycle drive sprocket because that's what it is. And we used a DC motor to control that. On the right-hand side where the throttle is, you can see the throttle there. We attached a linear actuator to that. And also we have a dead man switch. If things start to go bad on the water, we wanted a way to kill the outboard motor so that we didn't have a potential problem getting worse. We teamed all this up with an onboard data acquisition ship or a data acquisition system. And we had 2 parts to it, one on the test boat, which you've seen, and then one in a chase boat, and you'll see that also. So we had real-time data. We knew forces measured in G's, we knew direction, we knew rate of turn, we knew speed through the water, and we had all time stamps on that in real time. So the testing or the design of that system was again unique, hadn't been done like this before, and it turned out to be very successful in the end.
Bill, how long did it take CED to come, or you guys to come up with the design and also to physically implement the design onto the boat?
Great question. I'm kind of laughing because you know, with every design, it starts and stops. You try something, it doesn't work, and you go back to the drawing boards. But if I added up all the time, and deleted all the dead time. It was probably 2 solid weeks of engineering work to design this. And you say, well, it doesn't look that difficult. And you go, well, yeah, it doesn't when it's all done. But there were hiccups. Things didn't work the way we wanted. So we tested all this in our parking lot, basically where you're seeing that boat right now, to make sure it worked. And we took it out on the water to make sure it really worked out there. What do we mean by work? When we put a command in to steer, it did what we asked it to do. When we put a command in for throttle, it did what we asked it to do. And when we commanded it to stop, it did all those things. So that took some time.
Okay.
So now, here we're underway. We got plenty of help. What did we do here? You can see the chase boat there, chase slant command boat. That's in the middle. The test boat, you'll recognize that. That's on the right-hand side. And then we had range safety. CTO provided an opportunity to clear the range to make sure nobody was there. And also in the extreme, we didn't need it, but we had to plan on it, that if something happened to the test boat or another boat on the water, we wanted CTO there to help us should the need arise. Turns out we didn't. That was good, but it's better to be prepared than not. Now, we'll go ahead and start this video. This is, you can see, it kind of makes people a little crazy. That's the boat. It's about to be underway. You'll see in the video, and there's nobody on board steering it. So here you see we're going to come up on plane. What you don't see is a chase boat astern of this boat. But it's pretty neat. We're on the South River in Annapolis, Maryland. The principal river in Annapolis is the Severn. South River, kind of a catchy name, is just a little bit south of that. So that's the perspective of what we were able to do. And you can see all the control features on there a little bit differently than we saw before. Now, here, this one, and I'll start the video in a moment. When we wrote our protocol, we wanted to make sure we understood the boundaries of this problem. And so to start with that, we start out with a shallow turn at slow speed, and we work our way then up to faster speeds and a more robust turn. And so it was an iterative process, and we had in our protocol various steps to the speed and various steps to the rate of turn. And then, of course, this whole time we're copying down the data. So here's the video that shows a shallow turn, and you're not going to see any problems. There's a chase boat. It'll clear the screen in a moment, and you'll be able to see the actual test boat turning. And the person sitting in the chair in that chase boat, that happens to be Brian Goodwin, who's on this webinar with us today.
Way to go, Brian.
So there's the boat turning. Said, looks pretty normal. No real problems there. That's good. So again, what we're trying to do is figure out the envelope, the operating envelope for this boat. When is it good and when is it bad?
Bill, as I watch this video, a question comes to mind of how far away could you get remotely and still operate the boat?
You know, I don't, that's a good question, Tony. I don't remember the exact distance, but I'm going to say it was 100+ feet. We tested that in the parking lot to see how far we could get away from the boat and still have it respond. But I'm going to say somewhere in the neighborhood of 100 feet. I may be off on that, but clearly there was a distance beyond which we didn't want to go.
Yeah, you don't want to lose control.
That's
the kill
right.
switch.
Yeah, exactly. So now, let me get to the next one here. So this one, now we're going to fast forward. This is a sharper turn, and you're going to see a swap end. So we went from the no problem. Now you're going to see what I talk about when I go, it swaps ends. And there it is. Okay, now we've run a couple of these together. Here's another version of it. same result. And then I have a third one. You can see CTO there. Now, there are a couple takeaways from this, and we'll show you some stills in a moment. But remember what I said at the beginning, it would swap ends. You saw that 180-degree turn, a rapid deceleration. So what does that mean if you're thrown from the water or thrown from the boat? You're still in close proximity to that boat, and you're no longer in the boat, you're in the water. The propeller's still turning, the boat's still moving. So there's opportunity, hopefully you're wearing a life jacket, there's opportunity to either drown if you're not wearing a life jacket because you can get struck by the boat. You could have blunt force trauma by the boat, or you could be struck by portions of the outboard motor and or the propeller. So there's blunt force trauma, there's drowning potential, there's propeller strike potential because that boat is now very close to where you were ejected from the water or ejected from the boat. So here's just some stills, and this is the start of a steady turn. You go, everything looks pretty good. Nothing unusual there at all. But here's what happens. Look at that abrupt loss of control. You go, the head you see there on the left and right side, that's in the chase boat. The boat starts to turn, and then rapidly it departs. Meaning it moves 180 degrees and rapidly decelerates. So that gets you an idea of what happens if you're ejected from that boat. Now, the other thing that happens is as a boat's turning left, which way does the body want to go? Well, the body tends to move to the right, to starboard. The boat's turning port, the body wants to move to starboard. And so there's forces that push you there, and we measured those in G forces. What we found with the data, not surprising, is that when the boat swaps ends, if the G force is pushing you to starboard because you're in a port turn, the G force reverses and then goes to port. And the difference is well over a G when you add up both directions. And so you can see where an unalerted passenger or even the operator, an unalerted person, if they're not holding on for dear life, they're going to get ejected. That's what our data showed us. And there you see that rapid deceleration. You can see where the turn was, and you can see the boat didn't continue. Now, those who have been on boats know boats don't have brakes. So when you ease off on the throttle, pull the throttle all the way back, what happens? The boat just keeps going down range, wherever you were headed. Or if you're in a turn, it'll continue to go in that turn. But this one didn't. You can see that. Look at that wake. It doesn't continue. It stops. So it's a very rapid deceleration. Now, I don't want to make you a naval architecture expert, but I wanted to just show you kind of what was going on. So let's look at these pictures on the left and on the right. The upper picture on the left and the right. You're going straight, that's the upper left. And there's a tunnel in there. We saw that tunnel before, and that tunnel starts about where the arrowhead is, and that yellow arrow, right about here. That's where the tunnel starts, okay? And you see it over here, that tunnel is all full of water. You go, that's really good, not a problem. Now let's start to turn. Here's the turn. The water separates, the flow of the water while you're turning, it separates. And the lower unit of the outboard motor starts to ventilate, meaning it's not in water anymore. See it over here? And what provides the ability to move the boat through the water and what provides the ability to turn? It's the same thing. It's that outboard motor. So you place this boat into a turn, the tunnel starts to ventilate, you lose control of the ability to control the boat. So the challenge then is to say, well, this is great. Some of these boats are out on the water. How do you fix them? We know what it does. We have data that shows what it does, and it's really not complimentary if you're a passenger. So how do you fix it? So along with our naval architecture person who's a professor at the Naval Academy, specializes in small boats, we developed some skegs. I don't know if you know what a skeg is, but it's this appendage right here. It's a certain length that goes forward and aft, in this particular case, aft to forward. And there's one on the starboard side, one on the port side. And those are physically attached to the underside of the Texas Flats boat. And the idea behind that was to provide larger forces at the stern with those skegs, so the boat would not spin out. So we then tested a boat with that on there, and the skegs were successful. Now, all skegs are not created equal. We designed them. The initial set were pretty big. They weren't very appealing. We put a smaller set on, but the bottom line is it was effective. It meaning the skeg.
So all in all, Bill, what you're saying is that we tested the boat. We proved in fact, really was an issue with the design of the boat, and we came up with a solution that works in order to fix, without, like you said, without coming up with a whole brand new mold, came up with a solution to actually fix the problem in the field.
Yes, absolutely. Now, you know, when I said without changing the mold, in theory, successive or follow-on boats, the mold could be changed such that the skeg is part of the mold rather than having to add it later. But the point is, for all those boats that are on the water that the owners wanted to continue to use, there is an opportunity to have skegs installed such that their boat would become stable and not exhibit those dynamic instabilities that you saw in those videos.
Okay. Well, I got a couple questions that came in. First one is, did a CD do any comparative testing, like legacy boats, like large manufacturer boats, as compared to this Texas style boat that we tested?
We did. And you know, the whole form can be a little deceiving. You saw it on the trailer, but yes, we did. And you know, in the extreme, you can probably get, I won't say any boat, you can get recreational boats to spin, but you have to work at it. The problem with this one was you didn't have to work at it. It did it under conditions that normally it wouldn't do. Tony's smiling because he likes jet skis. Can you get a jet ski to stand on its bow? Sure you can. And people do that all the time. But you know what you're doing, you're holding on, and you're the one that caused it to do that. But the jet ski doesn't do that in a normal turn. And that was the problem with this one. So yes, we did. Long answer to a short question. We did test more legacy manufactured boats.
Okay. Another question that came in, I'm looking at here, is basically, I know we just talked about it. Well, actually, watching the video, did we factor in weight on the boat? Because I didn't really see, you know, you look at the boat, there's no one on the boat. Did we factor people like as far as weight on the boat?
Yes, we did. And that was part of our protocol. In addition to what I said before, of varying speed and varying the rate of turn, we also put weight on the boat. Forward of the center console, weights in different locations and different amounts to see if that had any net result on the envelope. And of course it did. And we could go through all the data. That's really not what I wanted to do today on this because it's a short webinar. But yes, we varied the weight, and that variation in the weight had an effect on our data.
Okay. No, yeah, that's good because when I first watched the video, I didn't see that there's anybody on it, so I was curious if you factor in the weight.
Yeah. There were other videos that showed that. We had a lot of video, and I picked the ones that really illustrated the point the best.
And I guess the last question one of the other questions that came in was, so hey, you own one of these boats, where could you take it to get it retrofitted to be safe? Because obviously you own one of these boats and you just watched this presentation, you're not looking to go take that out in the water without making sure it's safe the next time you take it out.
Right. Any competent recreational boat yard should be able to make the modifications that we made. Again, They don't look that pretty when they're sitting on a trailer, but you know, when it's in the water, you probably don't notice it. But a competent marina should be able to do that.
Okay. Well, we're we said 20 minutes. We're at 26 minutes, so we'll wrap it up for now. I want to thank everyone for attending the webinar. We hope you found it interesting and informative. If you would like to contact CED Technologies, you can visit our website, www.cedtechnologies.com, or you can give us a call at 1-800-780-4221. Hope everyone has a fantastic day. Thank you very much. Take care.
All right. Thanks, everybody.